This lesson will cover periodic trends. This is going to be a two-part lesson. Today we are just going to focus on trends as we go across a period. So as a reminder, periods are going to be those horizontal rows across our periodic table. So to explain periodic trends, we need to first start by talking about effective nuclear charge, called ZEF. So Z for nuclear charge and F for our effective nuclear charge. So what is ZEF? ZEF is the measure of the attractive force between the nucleus and valence electrons. Remember that the nucleus is overall positively charged, and we know that valence electrons are negatively charged. So there's going to be an attraction between our positively charged nucleus and our negatively charged valence electrons. The closer an electron is to the nucleus, the stronger the attraction. Which should make sense. The closer those oppositely charged particles are to each other, the stronger that attraction there will be. Also, more protons leads to a stronger attraction. The more positively charged protons you have attracting those valence electrons, the stronger that attraction will be. For this class, you won't have to calculate ZEF, we just need to understand the relationship. But if you were to calculate ZEF, the equation would be Z minus S, where Z is equal to the number of protons and S is equal to the number of inner electrons. If we were to calculate ZEF, the smaller the ZEF value, the weaker the attraction. And then vice versa. If we calculate ZEF, the larger the ZEF, the stronger the attraction. So let's look at this in sodium versus magnesium. So sodium and magnesium are in the same period. They're both period 3 metals. And we're going to look at what happens as we move across the period. Since they're both in period 3, they both have 3 energy levels. Sodium is atomic number 11. So sodium has 11 protons and 11 electrons. Since sodium is in group 1, it has 1 valence electron. Magnesium is in group 2. So magnesium has 2 valence electrons. The electrons in pink are what we call inner or core electrons. The electrons that I drew in purple are in the outermost energy level, so we call those valence electrons. So if I were to calculate my Zeph for sodium, sodium is atomic number 11, so it has 11 protons, and then I'm going to subtract out the number of inner electrons. Sodium has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So its Zeph would be a +1. If I were to do the same thing for magnesium, magnesium has 12 protons. It also has 10 inner or core electrons, so its Zeph is going to be +2. Sodium has a smaller Zeph, therefore it has a weaker attraction. So that's going to be important to understand why certain properties occur, why there are certain trends as we move across a period. So the first property that we are going to talk about is atomic radii. The trend. Atomic radii decreases across a period. So as we go across a period, the atomic radius gets smaller. Well, why does that occur? Zeph increases across a period, which means the attraction gets stronger. We saw that when comparing sodium to magnesium, as I go across the period, the Zeph is increasing. If the Zeph is increasing, the attraction is getting stronger. So magnesium has a stronger attraction from its positively charged nucleus to its valence electron. Well, how does that affect atomic radius? That means those valence electrons, that attraction is stronger, so the valence electrons get pulled in closer. Which decreases atomic radius. So here is a picture of 2 period 2 elements, beryllium and oxygen. Let's look at where those are in the periodic table really quick. So we're comparing the period 2 elements, beryllium to oxygen. As we go across the periodic table, Zeph increases, which means radius decreases. So I see that the atomic radius of oxygen is much smaller than beryllium. Again, the reason why these positively charged protons are going to be attracted to our negatively charged electrons. Well, as Zeph increases, as we have more protons, it's going to cause a stronger pull on those electrons. If I have that stronger attraction, those electrons get pulled in tighter, so my atomic radius is going to go down. You should also be able to compare the atomic radius of an atom to its ion. So the next trend for atomic radius, positive ions are smaller than their respective neutral atom. The reason why positive ions, which again we call a cation, cations lose electrons, so their valence electrons are in a smaller energy level. So let's draw what this looks like so you have a visual. We're going to look at lithium. So my lithium ion is smaller than the lithium atom. So if I were to draw a lithium atom, lithium is atomic number 3. 3 protons, 3 electrons. Well, what happens when lithium loses an electron? It loses an entire energy level. Here, my valence electrons are in the second energy level. When lithium loses an electron, its valence electrons are in the first energy level. So now the electrons are in a smaller energy level, so I can see that the lithium ion is much smaller than the lithium atom. So this holds true for all positive ions. Positive ions are going to be smaller than their respective neutral atom. We are going to have the opposite trend when it comes to negative ions. Negative ions are larger than their respective neutral atom. Well, cations lose electrons. Anions gain electrons. So there are more electrons, but the same number of protons. So that means they aren't held as closely. So when an atom gains electrons and it becomes an anion, we have the same number of protons, but now there's more electrons. That means it's going to decrease the attraction, which causes that atom to get larger. Let's look at a few examples. Rank the following. From smallest to largest. Alright, so first one, we are looking at all atoms, no ions. I have fluorine, nitrogen, and oxygen. Fluorine, nitrogen, and oxygen are all in the same period. So remember our trend. The atomic radii decreases across the period. So if I were to rank them from smallest to largest, and it decreases as we go across, fluorine would be the smallest, followed by oxygen. Nitrogen would be the largest. I always remember this as the largest atom is on the left. Largest and left both start with L. So nitrogen is the farthest to the left. It is larger than oxygen. Oxygen is to the left of fluorine. Oxygen is larger than fluorine. B. B gets a little trickier because now we have an ion to take into account. So first, let's compare phosphorus and sulfur. Larger on the left. Phosphorus is larger than sulfur. Sulfur is smaller than phosphorus. Now we need to compare the phosphorus atom to the phosphorus ion. The ion is negatively charged. Negative ions are larger than their respective neutral atom. So the phosphorus ion would be larger than its phosphorus atom. Last one, now we're going to look at a cation. So first, let's compare the two atoms, sodium, magnesium. Larger on the left. Sodium is larger than magnesium. Now I want to compare the magnesium ion to the magnesium atom. Magnesium is positively charged. Positively charged ions are smaller than their respective neutral atom. So the magnesium ion would be smaller than the magnesium atom. The next trend. Reactivity. Reactivity of metals decrease across a period. And again, all of these trends across the period we want to relate back to Zeph. So we know that Zeph increases across a period. So that means as we go across a period, the electrons are held tighter. Which makes it harder to lose electrons. So if I were to compare potassium and calcium, potassium has one valence electron, calcium has two valence electrons. As I go across the period, the electrons are held tighter. So it's going to be harder for calcium to lose its two valence electrons than it is for potassium to lose its one valence electron. Since potassium can more easily lose its electron, it's going to be more reactive. Let's look at an example for reactivity. Rank in order of increasing reactivity. And let's look at magnesium, aluminum, and sodium. So the trend is that reactivity decreases across a period. Reactivity decreases across a period. That means aluminum would be the least reactive, sodium would be the most reactive. So if we're going to rank them in order of increasing reactivity, aluminum would be the least reactive, Sodium would be the most reactive. Last trend is called ionization energy. Ionization energy is the energy needed to remove an electron. Our trend. Ionization energy increases across a period. You might see some subscripts like IE1. Ionization energy is, IE1 is the first ionization energy. This is the energy needed to lose one electron, or the energy needed to remove an electron from a neutral atom. If I had IE2, this would be how much energy it needs to remove a second electron. So this would be the energy needed to remove an electron from an ion with a 1+ charge. Each succeeding ionization energy is larger than the preceding ionization energy. So it's going to take more energy to remove the second electron than it will from the first. Let's look at an example for ionization energy. Let's say you were told a period 3 element has the following ionization energies. And we have a little table: IE1, IE2, IE3, and IE4. And then we had some ionization energies listed in kilojoules per mole. So remember we said each succeeding ionization energy is greater than the one preceding it. So we can see that as we remove more electrons, it's going to take more energy. So first, you need to determine the number of valence electrons. So there's an important trend to figure this out. It is much harder to lose an inner or core electron than a valence electron. So we can pretty easily lose valence electrons. Remember, atoms want to lose valence electrons in order to follow the octet rule. But once an atom loses all of its valence electrons, and it now has 8 valence electrons in its outermost energy level, it doesn't want to lose any more. It is going to take a lot of energy to lose that inner core electron. So your key is to look for the biggest in ionization energy. So I see a huge jump here. About 2,800 kilojoules per mole up to almost 12,000. That is a huge jump in energy. That means that we can relatively easily lose 3 electrons. That means this 4th electron is probably that first inner core electron. So that leads to the conclusion that this element probably has 3 valence electrons. We can pretty easily lose the first 3. Once we get to the 4th, it's going to take a whole bunch of energy. That means that the 4th electron is probably an inner core electron. Once you know the number of valence electrons, you should be able to identify the element. And we need 2 pieces of information to do that. First, we need to know that it's in period 3. Next, we need to know that it has 3 valence electrons. So I can head to my periodic table. I can find the period 3 element that has 3 valence electrons. This element is aluminum. I'm going to draw a quick Bohr diagram for aluminum. Here's my nucleus. It's a period 3 element, so I know I have 3 electron shells. Atomic number 13. So I would have 13 protons, 13 electrons. So IE1 would be how much energy does it take to lose this first electron? IE2, how much energy does it take to lose the second electron? IE3, how much energy does it take to lose this third electron? Well, look at what happens once you lose those 3 electrons. Aluminum loses that entire energy level. Now, aluminum has 8 valence electrons. It doesn't want to lose another electron. Let's say this is the 4th electron to lose. Since aluminum has its 8 valence electrons, it's following the octet rule. It's going to take a lot of energy to lose that 4th electron. So that is your key for these types of problems. Figure out where you have the biggest jump in energy. The electrons that are more easily lost are all going to be valence electrons. The first electron that is much more difficult to lose is going to be your inner core electron. Once you know what period the element's in and how many valence electrons you have, you can use your periodic table to identify it.